We often think of math as just numbers and equations, right? But what if I told you that hidden inside some of the most abstract algebra are these incredibly beautiful, perfect geometric shapes? Well, today we're going to go on a hunt for them. We're finding the hidden geometry inside complex numbers.
Okay, just look at this. You ask a simple algebraic question, what are the 5/5 roots of this one number? And the answer you get isn't just a boring list of values, it's a perfect pentagon. How does that even happen? This isn't a coincidence or some weird math fluke. It's baked into the very nature of complex numbers, and we're about to pull back the curtain and see exactly how it works.
So, that brings us to the big question for today. How on earth can a single number have three totally different cube roots? I mean, the cube root of 8 is just 2, right? Well, in the world of complex numbers, it's different. And what's even crazier is why do those three answers line up to form a perfect equilateral triangle? That's the puzzle we're going to piece together.
To get to the bottom of this, we first have to understand the geometric rules of the game. It turns out these amazing shapes don't just happen by chance. They follow a really elegant and predictable pattern every single time. Let's break it down.
So there are basically three simple rules at play here. First, equal magnitude. All that means is that every single root is the exact same distance from the center. So naturally, they all have to lie on a perfect circle. Second, rotational symmetry. The roots are spaced out perfectly at equal angles from each other around that circle. And when you put those two things together, you get the third rule, polygon formation. If you just connect the dots, you always get a perfect regular shape. 3 roots make a triangle, 4 make a square, 5 make a pentagon, and so on. It's just a beautifully elegant system.
Okay, so seeing the beautiful picture at the end is one thing, but what's the actual math doing behind the scenes to create it? Let's stop thinking about it as just a dry equation and frame it like the quest that it really is.
Here's the goal, plain and simple. We start with a number. Let's call it Z. We're looking for all the numbers, we'll call them W, that you can multiply by themselves n times to get back to Z. So for our triangle mystery, we're trying to find every single number W that solves the equation W cubed equals 8i.
All right, we have our quest, and every good quest needs a key, right? A special tool to unlock the final treasure. Well, in our case, that key is a really powerful formula that's going to do all the heavy lifting for us.
And here it is, De Moivre's root formula. I know, it looks like a beast. You see cosines and sines and letters all over the place. But don't worry, every single piece of this formula has a very simple, very visual job to do. This thing right here is the engine that draws those perfect shapes. So let's break it down one piece at a time.
First up, you've got R. This is super simple. It's just the magnitude. The distance our starting number is from the very center of the graph. Think of it as setting the radius of that big circle that all our answers are going to live on.
Next, we have theta. This is just the angle of our original number. It tells us which direction it's pointing in, and it gives us the starting position for our very first root. It's our launch point on the circle.
Now, n is the easy one. It's simply the number of roots we're looking for. Are we looking for cube roots? Then n is 3. Fifth roots? Then n is 5. This number also tells us exactly how many corners our final shape is going to have. For our problem, n is 3, so we're hunting for a triangle.
And finally, we have K. This is the magic ingredient. Think of K as a little counter that starts at 0 and ticks up for each root we want to find. As the ticks up, it perfectly rotates us around the circle to the next spot, landing on each corner of our shape one by one. This is the variable that guarantees that perfect even spacing.
All right, theory time is over. We have our formula, we know what all the little bits and pieces do, so now let's actually put it to work and solve our original mystery. What are the 3 cube roots of 8i?
We're going to follow this straightforward 4-step plan. First, we'll identify our starting number. Second, we'll convert it into what's called polar form. That's just that distance and angle language we were talking about. Third, we'll plug those numbers into our big formula. And finally, we'll crank the handle and calculate our 3 answers. Okay, let's do this. Our starting number, our Z, is 8i. Now, if you picture that on a graph, it's not left or right at all. It's just a point 8 units straight up. That makes finding its polar coordinates super easy. The distance, r, is just 8, and the angle theta is 90 degrees, pointing straight up. Easy enough.
Now for step 3. We literally just take the values we found and plug them into the formula. We're finding cube roots, so we swap n for 3. Our distance r was 8, so that goes in. Our angle theta was 90 degrees or pi over 2 radians, so that goes in too. And just like that, our all-purpose tool is now locked and loaded for our specific problem.
And this is where our little counter, k, comes in to do its job. Since we're looking for 3 roots, k is going to take on 3 values, 0, then 1, and then 2. Each one of those is going to spit out one of the corners of our triangle. Let's find them.
First, we set k equal to 0, run the calculation, and boom, we get our first root, the square root of 3 plus I. Next, we let our counter tick up to 1, plug that in, and out pops the second root, negative square root of 3 plus I. And finally, we set k equal to 2, and we get our third and final root, negative 2i. And there you have it, our 3 distinct algebraic answers.
And here is the payoff. This is where it all comes together. On the left, you see the 3 answers we just calculated. And on the right, that's where those 3 points actually land on the graph. And look at that, a perfect, symmetrical, equilateral triangle. The algebra didn't just give us numbers, it drew us a picture. Mystery solved.
So you might be thinking, okay, that's really cool, but why does this polar form, this way of thinking in terms of distance and angle, work so perfectly? What's the big secret?
Well, the absolute beauty of polar form is that it makes multiplication and division ridiculously simple. To multiply 2 complex numbers, you just multiply their distances and you add their angles. That's it. To divide them, you divide their distances and subtract their angles. It turns complicated algebra into simple arithmetic. And since finding a root is basically multiplication in reverse, that's why the angles get split up so perfectly, creating these amazing, predictable shapes every single time.
So if there's one thing to take away from all this, it's that math can be incredibly visual and beautiful, even when it looks abstract. We started with a simple number, 8i, and we discovered that its 3 cube roots were hiding a perfect triangle. So I'll leave you with a little puzzle to think about. If we took the number 32 and found its 5/5 roots, what incredible shape do you think those answers would create?